is applications. And that might sound like it's going to be horrible, but it's not. You know, the normal kind of applications you get would be radical equations that you have to solve. You know, like that's what we've done with everything else, right? When we did rational things, we had to do boat sailing uphill and boat sailing downhill. These questions, trust me, I hope you believe when you're finished, are very easy. So there's a surprise. You might have thought, oh God, we're now going to have to do word stories that are going to involve square roots and are going to be massively ugly. And the answer is, not really. We're going to do word stories, mostly with triangles, that are very easy to do. So it's going to be a little bit of a pleasant surprise. And I don't expect that will take us too long. And then the last thing we're going to do, the second thing, is we're going to look into, and this is we're going to spend a lot of time on, are called complex numbers. Okay, so that's our kind of roadmap for today. So let's start with applications. Almost every question, in fact, I can say, I think, with a fair degree of accuracy, all of them are going to involve this triangle, or family of this. Do you know these triangles are called right-angled triangles? I'm sure you've heard that term. Now, I'm going to call this side A, this side B, and this side C. And I think you may have seen this fella. A guy called Pythagoras discovered that there was a very simple relationship between the lengths of the three sides of a right-angled triangle. Does that look familiar? Maybe the letters are different, but if you've seen that's called Pythagoras' theorem. That's going to be the only guy that we're going to be using during every application, because the applications that they're talking about here are, I think they call them geometric applications. I'd probably call them right-angled triangle applications. So what you're going to get, you are going to get a right-angled triangle where they will tell you one or two sides, and your job is to find everybody else. That's pretty much it every single time. So there are going to be two flavors of this question. One of them is going to involve a triangle, a right-angled triangle, where these two angles are the same. If you have a right-angled triangle and at the same time these two angles are the same, wouldn't this side here be the same size as that side there? Agree? So that's a kind of special version of this. And then the other version is just going to be basically that. Now, when you have a version like this, and you know this side and you know this side, and I call it A and B and C, this relationship changes. If we say that these are equal, can't I just say A equals B, right? Because it's the same length. So it starts off as C squared equals A squared plus B squared. And then it's going to turn into A squared plus another A squared. And then it's going to turn into that guy. And we're going to use that fella to solve these triangles. And we're going to use this fella to solve these triangles. I'll just try out some numbers, show you what they look like. The questions are pretty much the same all the time. Find the missing sides. Whoops, find the missing sides. So, suppose I do a triangle and I tell you this guy here is 5 and this guy here is 4, and I ask you to find that side. If you call this fella A, you call this fella B, and obviously I'll call that guy C. C squared is A squared plus B squared. C squared is 5 squared plus 4 squared. 5 squared is 25, 4 squared is 16. C squared is 41. So far so good, wasn't really too painful. What do you think I'm going to do next to find C? I know C squared is 41. What do you think I should do next to just find out what number C is? Last chance? Agreed? Now, what does your answer look like? If the book does not mention anything to do with round off your answer to 2 decimal places, you know that kind of phrase? Leave it alone. Just write in square root of 41 in the box where you're meant to put your answer, right? If they say, I want the answer to 2 decimal places, which they might, and I'm sure they will from time to time, then you just got your calculator and you find out what the square root of 41 is, and you write it down to, let's say they wanted the answer to 2 decimal places. Does that seem reasonable? There's not an awful lot in these questions. I hope you'll gather that by the time we've finished. Now, there is a third possibility. Can you imagine that for a different group of numbers, the answer ended up being the square root of 40? Could happen, right? That's not considered the best version of this. So we're going to bring back a guy we've used quite a lot. Can't you simplify this square root? I don't have my little table at my side here, but hopefully I don't need it anymore. Can you see that that would be 4 times 10? And therefore you will write down 2 root 10 in the box where the answers go. So here is one example of the types of questions you're going to get. In this particular question, all the sides are different lengths. You're told A and B, and you're being asked to find C. Here's another question, looks the same, but it's slightly different. Let's suppose I tell you that's 10, and I tell you that's 4, and I want to know this guy here. So there's ABC. Start these questions the same way, I would anyway. Start them by writing down your formula, then put in the 2 guys that you know the length of, and then convert them to numbers. So don't leave them as squares, but convert them into numbers. You're going to end up, in this question at least, aren't you going to end up with a number that looks like that, or a situation that looks like that? Think of, as long as you do it to both sides, it's okay. So what might be a good thing to do to both sides in this question?
Subtract the 16.
Do you agree? And would you agree that the last thing to do would be to take the square roots of both sides? That might be the final answer, but not this time. 84. You're going hunting for a perfect square in somebody else, aren't you? I can see your thought processes as we sit here. It's not very big if you want to know what the number is, if that's a clue. Anyone found it? Two guys that give you 84.
4 and 21.
Okay. Which means that you're going to end up with 2 root 21. And if they want it as a decimal, you'll just go to your calculator and you'll turn that into a decimal. Depends on what they asked. So far, I'm Am I living up to the expectation that these questions are not difficult? Okay, so let's show you a version that looks like this. I'm not pretty badly drawn triangles, but pretend I can draw good. Do you notice that this one has the added 45 degree thing going on? So in these questions, won't A be the same size as B? So won't that make A 7? So now all I have to find is C, and the question is over. So we had this little thing here to do before we entered the main question. So let's see what we have. We have C squared equals 7 squared plus 7 squared. That's 49 plus 49. That's 98. Square root of both sides. That might be the answer, but in this case it's not. It can be simplified. I'm telling you it can be simplified. I guess I should check that it can be simplified. Yes, it can. Yeah. Do you know what it simplifies down to? How do you do it over here? What two numbers get you 98? It's actually quite a big number this time.
49 and 2.
Yeah. Do you know if you do enough of these, you'll start figuring out it's this guy? Yeah, in this kind of question. So 7 root 2. So this is an example where you're told that they're the same. You could be told that they're the same in a slightly different way. Do you know you can just put a little mark on both sides like that, and that means they're the same length? And they could have then told you that was 7 and ask you to find the other two guys, right? And I've forgotten a very simple thing. Do you know what this long sloping side is called? Because it is given a special name.
The hypotenuse?
Yeah. Just in case the question says, find the hypotenuse, right? Rather than say find C, just in case they use words. Now I've done every single combination that you're likely to see except one. So we're going to be looking at an isosceles right-angled triangle. That's what you call it when it's right-angled and two sides are the same, right? Isosceles right-angled triangle. And in this case, I'm only going to tell you that that guy's 10. Well, of course, and that they are the same size, because they are. And I'm going to call this A, I'm going to call this B, I'm going to call this C. And I'm going to start with this. I know C is 10. Now, I don't know what A is, so I'll call it A squared. I don't know what B is, but don't I know it's the same as A? So this guy here is going to get replaced by A squared. Can you see the logic of why I could do that? Its length's the same, right? Which means that this is 100, and these two get me 2A squared. So do you see how we work around the problem of two missing sides? Because when they're the same length, we call them both A. Okay, think about doing the same thing to both sides to eventually get A. So where am I going next? Hopefully it's obvious.
Divide both sides by 2.
And then would you agree you're going to take the square root of both sides? And I feel like a broken record here, but I'm going to do it again. That might be the end, because I know it will be for some questions, but not now.
25 and 2.
Yeah, and that ends up getting us 5 root 2. Is there a kind of flow to these questions? Like they all kind of go the same way, they just change the numbers on you? Are you getting that feel off these? That is pretty much all you need to do. So I'm going to give you 4 questions, one of each kind of version. And if we can do these and you feel comfortable about them, that's the end of that section. There's nothing else to worry about, nothing else to do. So the questions are all the same. Find all the missing sides in these 4 triangles. And I'm just going to use the little marks to mean same size. And in this case, I'm going to go 6, 8. In this case, I'm going to go 5. No, I'm not going to go 15, 4. In this case here, I'm going to go 3. In this case here, I'm going to go 8. There you go. Finish these triangles off. Find all the missing sides. I don't know how long it's get. I have to judge. 5 minutes? Maybe not even need that. We'll see. We about ready? Okay, here goes. In this first one, it's pretty much plug and chug. There's really no preparation that I can see. You're just going to replace this guy by 8, this guy by 6. Adds up to 100, doesn't it? So you actually get a perfect answer, which is nice when it happens. So 10. Now this second one, you put 15 here. You don't know A, and you put B squared here. That's going to get you 225, and A squared, why am I putting B there? I should be putting 4, there we go, plus 16. That's not going to work nice. That's 209 equals A squared. My gut feeling is I can't think of anything that works with 209, but maybe you found something I didn't. Nobody found it either? Then it's probably as good as it's going to get then, right? Now this one has 2 sides the same, right? So when I do the C squared, it's going to be 3 squared plus another 3 squared, right? They're both the same size. So that makes C squared equals 9 plus 9, which makes C squared equal to 18, which makes C the square root of 18. But I do know that one simplifies. Anybody want to tell us? Square root of 18. You try to say something, Mary?
9 and 2?
9 and 2, which ends up being 3 root 2 then, right? Okay, the last one. Don't know this one, don't know this one, but I know they're the same. So won't A squared be A squared plus A squared? So 64 is going to be 2A squared. Divide both sides by 2. And then you take the square root of both sides. And I'm pretty sure that square root of 32 can also be simplified. 4 root 2 eventually. Yeah. Well, that's pretty much everything you need to know. Do you feel comfortable about these guys? As far as the section before it is probably going to cost you a lot more headaches, you know, when you're trying to solve rational equations. There's a lot in those guys. I don't think there's a lot in the ones we just did. So, not bad. It'd be good if you could do every section in a half hour. This course would last 2 days, but it's not quite the same. Right, now let's look at our last topic. Okay. Has anybody ever heard about complex numbers? They appeared anywhere in your life, in your math life? So, would it be fair to say that for pretty much everybody that's here, that these are brand new? You might not even know what they are, right? Pretty obvious they're numbers. and there's something to do with being difficult or hard in some way, so they're called complex numbers. Well, let's give you a little history to where they're coming from. Very small, short history. If you go into what's called number theory, you'll find that there are all sorts of numbers in the world. The first kind of numbers were natural numbers. Pretty much every civilization in the world, the most primitive ones would start with these. Natural numbers are 1, 2, 3. Can you imagine a caveman would at least have to know how many kids he's got in case one of them get ate? Hey, 1, 2, 3, where's the other one, right? I've got 42 sheep, right? I gotta know how many sheep I've got, because if one of them goes missing, I know that I have to go looking for him in a cave somewhere, right? So you can imagine, as a counting system, that was the first counting system. And every society that we've ever discovered in the past, every single one of them, definitely had a counting system. Now, they didn't call them 1, 2, 3, you know, they called them un, deux, trois, because they were French, right? And they called them whatever it is because that was their language. But they all had 1, 2, 3. Then some bright guy, I believe it was an Indian actually from the Indus Valley, added one more number to the number system. He added 0. Now, what did 0 allow us to do? 0 allowed us to do place value. See, before you had 203, if you were a Roman and you counted using this system, you had to call it CCIII. The Greeks, I believe they used the letters of the alphabet, so it would be gamma, gamma, alpha, 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 or something, right? They had some. Do you know the drawback of not having 0? Could you imagine a Roman guy trying to multiply 203 by 105? Good luck, right? All the early societies who didn't have 0 had big problems with computation. In fact, virtually nobody knew how to do more than just rudimentary add and subtract. I guess in their everyday life, that was all you needed, right? I've got 42 coins, I'm giving you 3, whatever, that kind of thing. But we needed 0, and 0 allowed us to do decimals. And for a very long time, that was perfect. Until about, well, I'm guessing here, about 400 or 500 years ago, that was perfect. And then there was some business people who came on the market. This is when banks started. You might not have thought of this, but you know, for most of history, there weren't banks. I mean, there was money, but there wasn't banks. When you did a transaction, you borrowed money from one person and you promised to give it back. And if you didn't give it back, there were normally very dire consequences to it. Right? You would have contracts where he could take your house if you didn't pay back, right? Or he could take your daughter as a wife or something, right? You know, there were some bad consequences to this. There wasn't banks. And then people kind of needed banks, but banks had a real problem. How do you keep track of money that you owe people and money that they owe you, right? You had to have, you know, they basically had ledgers, and you know, it was in the black and it was in the red. You heard that? I'm in the red, and you wondered where that came from? Because they used different colored ink. And it's very cumbersome. At the same time, there were some business people who were Venetians. And these Venetians were great business people, right? They sent stuff and they collected stuff, right? They, you know, went to Asia and they got some cool stuff and they brought it back and they sold it to people in Germany, and they got German stuff and sold it to French, right? They were all over the place. One of the problems they had was bales of wool, right? You make a big bale of wool and it's meant to make, let's pretend it's meant meant to weigh £100. Big bale of wool. Well, you know, none of them weighed £100. Some weighed £99 and some weighed 102. And it was too much trouble or even effort to try and unravel it, pull out some wool and tie it back up again. So they just left them. But they put marks on them. And they put a little mark that said the equivalent of, this guy is too overweight. So if you get this one, you're getting £102. And then they'd have another bale next to it maybe, and it was a funny little mark. It wasn't that mark, but they had a mark that said it was 3 under. What that developed was the banking system said, oh, that's kind of interesting. Positive and negative. Right? So if you've got a bank account and it's positive, it means that's money is yours, right? They've got that money, but it's your money, right? You're in the plus. And I'm sure you've heard I'm in the negative. That's where they came from. So we got negative numbers. So we got numbers like -1 and -2 and 0, 1 and 2. I am getting to the end of the story, but it's kind of interesting. Negative numbers. Negative numbers are called integers. Now, we've got a guy called rational numbers. And they kind of happened round about the same time that whole numbers are. You know, like things like 3/4 and 5/7, right? And one of the main reasons that fractions got invented or get created was that sometimes there was a need to break something up into pieces. Like you had 4 children and you wanted to give them shares of your farm when you died, right? How many acres would each of my children get, kind of thing? Can you imagine? You might say, I'm giving all my sons 1/4 of my wealth, right? But it didn't always work that way. Do you know, you might have had a favorite and you're saying, I'm giving John 3/4 of my wealth and the other 3 riffraff, they're getting whatever's left. So can you see there might be a need for fractions of different amounts, different ways. And fractions got invented or created or used. And then everybody thought that all the numbers in the world were already discovered, right? Up to this point in time, couldn't you have 1? You could have 0. You could have -2. Couldn't you have fractions, positive and negative? You could even have decimals like 1.2, but isn't decimals really just a disguised fraction? It's 1 and 2/10. That's all it is. And we thought we'd got them all. And then somebody came up and said, oops, solve that. Now you might think, well, where did that come from? Can you imagine somebody says, I've got a square and its area is 2 square meters. What's the size of the sides? And what that ended up doing, and it freaked them out, is that x had to be the square root of 2, right? Radical, square root of 2. And the reason it freaked them out is there isn't a fraction in the world that's the same value as the square root of 2. The square root of 2 is a new number. It makes what we call the real numbers. Now, a real number is pretty cool. You can imagine it on a number line. A real number is any guy you want. So couldn't a real number be 1.2? Couldn't a real number be the square root of 3? Couldn't a real number be 3/17? And when we got to that stage, which is actually not that long ago, we thought we had found all the numbers in the world. And then some guy came and said, hey, let's solve that. Now, do you know what the answer used to be? It used to be, it's not real. Sometimes they would say it doesn't exist, but mathematicians have learned better. You know, every time you did something, it didn't exist until somebody figured it out, right? How do you deal with negative? Can you imagine a caveman trying to explain to a caveman who only needed to count his sheep and his kids what -2 was? It's not that you don't have 2 children. I mean, what do you mean I don't have 2 children? I mean, that don't make sense. Can you imagine the concept wouldn't really make sense to him, and it probably wouldn't be a worthwhile concept, right? Negative numbers don't matter to those kind of people, but negative numbers matter a lot to businesses, don't they? That's profit and loss, and negative numbers matter for temperature, and negative numbers, whatever. So what a mathematician did, and I wish I could tell you his name, but I don't think it was one particular guy, went and said, okay, let's pretend that there is a number that's not a real number, right? Not like any number we've ever seen in the universe, right? So it's not real. Okay, I'm going to call it a complex number. I'm going to call it something, right? And it is the solution to this. Well, wouldn't the solution be you take the square root of both sides? Now, I know that the square root of -1 is not a real number, but it is a complex number because I've decided that that guy exists. And not only have I decided that he exists, because I don't like writing the square root in -1 a lot, and secondly, probably because it makes people cringe, I'm going to call this number I. And the square root of -1 is a complex number, and we use the letter I. Its real value is the square root of -1. Now, what it isn't, it's not a normal number. Nothing in the world is going to measure the square root of -1 long. Right? It's not a number like that. It's a totally new number. It's a creation of mathematicians. But it's still a number. And in the math world, to be a number, don't you have to have some objects, right, complex numbers, that you can add, subtract, multiply, and divide? If you can do those 4 things to it, isn't it a number? Even if it looks weird. And if you do more math, you're going to find there's other numbers out there. And matrices can very often be considered numbers. That's another different thing. So we've got this new guy. So what about this fella? Because that's a full-blown complex number. Now, this is a complex number, but that's like the building block, right? That's like saying 1, right? This is a complete complex number. And they even have names for them. See this bit here, which is the 3 that we're used to, right? A normal 3, a real number 3. This is called the real part. And you see this 2, not the I part, but how many of the I's you've got. This part here is called the imaginary part. And when this was first introduced into the mathematical world, it got a lot of flack. A lot of mathematicians just looked at that and said, oh, come on, that doesn't make sense. That's not that's not real, right? I'm not going to try to joke there. They just refused to accept it. In fact, there were some really very bright mathematicians who just called this, phantom numbers. They're not really there. You can't do anything with them. It's just a figment of somebody's imagination. So I think that's why they called these imaginary, just to get a dig at them. Hey, if these guys don't real, right? If they're not real, they're imaginary, right? They're made up. We'll go with it. We'll call it that then, right? Just to show you off. Well, what are we going to be doing here? Well, in this section, we are going to look at how do you add, how do you subtract, and how do you multiply complex numbers, right? And there's going to be rules that are mathematical, sensible rules. And we're also going to do how to turn negative square root guys into imaginary numbers, right? Because imagine somebody said, okay, if you're going to call that guy I, what are you going to do about this guy? We can't start writing down all the letters of the alphabet. We're going to run out of them before we run out of numbers. Is there a way that this fella here is connected to that guy there? And the answer is yes. You could probably have a good guess at how it's connected because we've done this a lot. Can't you split this up as 4 times -1? And isn't the square root of 4 2? So it's 2 times that. But we don't like using that. We use I because it looks pretty. So that makes the square root of -4 is actually just 2 of these i's. Doesn't that mean then, oh dear and spice, my headphones are giving me the nonsense. I'll keep going. We'll have a little break and I'll go and hunt out another pair. I got the batteries low. Do you hear it when it says batteries low? Because I hear it. Huh, okay. So can you imagine any negative square root can be turned into a version of I? So let's see. Won't that one be 9i? That one, you can't really do much about it except square root of 6. Some people like to write the I at the front. Some people write it at the back. I like to write it at the front. It just looks better. What about this fella? Well, technically speaking, I guess he's that guy. But you should be able to simplify it, and if you can, you should. I think we've done enough square root of 20s in our life to just know what the answer is. Anybody want to chuck it out? Square root of 20. You may have to hit the spacebar mark because I can't hear you.
2 square root of 5.
Right, and you put the 2 at the front and the square root of 5. Does it kind of make sense that the number 2 should go first, then the I, and then finish with the square root? It has a kind of shape to it that pretty much most textbooks will agree. So far, it's good. So if I gave you a square root of an ugly negative number, would you be quite comfortable at turning it into some version of I? Okay, so let's start with adding. Suppose I had 7 plus 2i, and the only reason I'm putting brackets around them is to emphasize that's a complex number. And I want to add 3 plus 5i. Now, from what I've asked at the beginning of today, nobody's actually seen complex numbers, so you're going to be like the first people. Imagine you're the first people to figure out how to deal with this problem, right? You've got to be able to add complex numbers, right? If they're going to be called numbers, you've got to be able to add them, right? What would seem a sensible way to add these two guys together? Don't go weird on me, just go obvious on me.
Combine like terms.
Yeah, so combine the real parts and get 10. Combine the imaginary parts and get 7. In fact, isn't it helpful to have names for them so you know what I'm talking about? That's the answer. Kind of obvious, kind of intuitive. You know, that's how I would do it if I was a person in charge of the rules, and it works perfectly well and it's mathematically consistent. This question should not be difficult based on the previous answer. If you want to subtract two complex numbers, shouldn't you subtract the real parts and subtract the imaginary parts? So here goes. 7 take away 3 gets me 4. And 2i take away 5i, I believe that gets you negative 3i. And it's okay to have plus 2i and negative 3i. They're totally fine complex numbers. We comfortable with those guys? Let's throw in a couple of a weird one. How about this? Now, if you subtract the real parts, you get 3 take away 6, which is -3. And if you subtract the imaginary part, okay. How's this going to work? Five I take away 5I. What are you going to get out of that? I think there's two possible answers here, isn't there, really? They're both the same, kind of, but one's good and one's not so good. Evan, what you got?
0.
Yeah. Now, you could write 0. You could write 0I. Or you could just not bother to write anything. Agreed? And I don't think it is too big a leap that we just write -3. When you combine like terms, you never say 0x, do you? You never even say 0, don't you? Just leave it blank because it's gone. There's none of them there. So that rule is still true. In fact, isn't it a bit like saying 3 add 5x, take away 6 add 5x? Isn't it kind of the same kind of math as that? You feel comfortable about add and subtract? Do you know this is going scarily fast? I haven't seen too many weird faces. You know, I'm in pain. What the heck is he doing? Are we good? Or am I just picking up the bad vibes here? The wrong vibes? Well, one's happy, so I'm saying, Evan, are you comfortable with so far so good? Mary, is this so far so good, right? Well, we know how you add and subtract, so that's 2 of the 3, right? So what's left? Multiply. Yeah. Multiply, maybe not so intuitive. I'll keep everything positive for a little while before we start moving into scary stuff. That's basically, I guess I could put a little multiplication dot in the middle. Isn't that how you multiply things? Have you noticed that putting brackets around them is actually very helpful for multiplication? How do you think I'm going to tackle this?
Well,
Yeah, FOIL. Three times 4 gets me 12. The outside. Oh, what's 3 times 3i going to get you? 3 multiplied by 3i. What's that going to get me?
9i.
Yeah. But we're not totally destroying the algebra that you're used to, are we, really? We're just adapting to a new situation, right? So 3 times 2 is still 6, right? And 3 times 2i is still 6i, and all the other combinations that you would expect. Now, if you do the inside, then would you agree that's going to be 8i? And then the awkward one. 2i times 3i. Now, if we follow the usual rules of algebra, shouldn't we call that 6i squared?
Okay, you should be looking right now at our homework, 7-7 homework, right? Complex numbers. And basically, we're just going to go through some of the examples. We've covered most of it already. And then I'm going to finish with some more complicated multiplications, a distributive law, and a few other bits and pieces. And that should take us to the end. So, oh, it doesn't help when you see the answer. There we go. So let's go. First thing, the number I, which defined as that guy, is one of these things, and it's an imaginary number. A number is any number that can be written form is called a complex number, right? When you stick a 4 plus 3i, that's the full name. So imaginary is just for the I, but when you do like 2 plus 3i, the whole combination is called a complex number. And in this case, isn't 4 called the real part? And 7 is called the imaginary part. So that's just us going through the vocabulary. So nothing too bad here. And oh, I guess I haven't done this. If you wanted to write this separated, then wouldn't you have to call it 9/5 and then plus 11/5 I? I am very sure, and I want to make sure what I say in them. Do you see how there's an I button here? That's the button that you have to do. I've got a sneaking suspicion if you hit the I on your keyboard, it's going to say you're wrong. It needs that special I, right? The real complex number I, right? That one. So be careful about that. Because you could do the questions and you get, how come every single damn question I'm doing is wrong and I'm doing it exactly how you did it? And it's simply just you wrote the keyboard I and not the special I.
The keyboard I works for me.
It does. Oh, thank goodness.
Yeah, it works
Yeah,
for me
it
too.
works.
At last, WebAssign has finally done something sensible. So I guess my question is, why did they bother even having it if they weren't going to use it? But whatever, I'm not going to argue with that. I'm pleased. And would you agree this guy we've covered, is it not 7i? Agree? 2i, nothing really. A lot of these questions, would you agree, they're very fast. You look at it, you do it. Let's move on a little bit, and that's a good point for me to stop. Let's show you. Although I'm pretty sure you could probably figure it out without me doing it with you. But let's figure out how you deal with some fraction situations, right? Suppose you're being asked to simplify this negative square root. The fact that it's negative, I mean, if you want to see the working, I guess the working looks like this. Do you see how you just pull the negative one out as a single item? In which case, it now becomes that, which now becomes that. But I would hope after a while you would just look at that and say it's got an I at the end, right? Is there anything I could do about this fella? Yep. In this case, we agree square root of 9, square root of 2, so there's your answer. It's another weird one. The negative of the square root of -4. And I guess to be able to solve this, you have to realise the priority. In other words, what things should be done before you do other things. In a question like this, ignore that negative. do this first. Won't that get you 2i? Right, square root of negative 4. And then do the negative. Don't do this. Negative, negative, square root of 4, answer is 2. You see, I took this negative and did it first, and it generates, it might seem reasonable that it should generate that, but that is just not right. That makes sense. There's one way to do it, and there's another way not to do it, and the only one that works is do this first and then worry about the negative. Yeah. How about a distributive law? Now, you could leave these guys as they are and try the distributive thing. I suggest very strongly that you don't, because typically if you do it that way, you tend to lose an I, right? That's a joke. Do you know that Scrabble is all fun and games until someone loses an I? I'm letting that one sink in. That is a good joke. I'm not letting that one just go by as a nod and then forget about it. Did you get it? Okay, now I will move on. Okay. What I strongly suggest that you do here is you turn everybody into their I version. Then you can do the distributive. 2 times that gets you 6i squared. 2 times that gets you 10i. And then, when you see an I squared, we already just did it once. What number, and it's a number, does I squared become?
-1.
So, can you see our final result? Are we good? So, I think adding and subtracting of complex numbers is really not a biggie. Would you agree? It's kind of, you would have done it that way even if nobody told you. It's kind of, it seems a reasonable way to add 2 complex numbers or subtract 2 complex numbers. Does multiplication using FOIL or multiplication using the distributive law seem reasonably natural? It's not like you're breaking the rules. You're just following the rules and adapting. Does that seem reasonable? The best thing to do, as I say, I'll repeat it again, is turn all these guys into I's. If you don't, you really shouldn't show students the wrong way to do something. But if you don't, I'll show you what can happen. People will go square root of -4 times square root of -9. And they will go -4 times -9 square root of 36. 6. Do you see how you lost the I? Don't do it, right? Turn everything into I's. Your life will be much simpler because if it's an I, it's an I. If it's an I squared, it becomes -1 and then you're finished, right? So there are only like 2 possibilities. Well, theoretically, 2 possibilities. So let's see if I can make your head hurt. I on its own is I. That is just a complete mistake. We've already done I squared, and don't you get -1? I cubed. Can you imagine in some worlds you might multiply I by a third time, right? We may want to do it. So we have to figure out what it's equal to. Any suggestions for I do it?
+1?
It could be. It's not, but I totally understand. It could be. Any other suggestions?
-I.
Yes. Let's show you one way of thinking about I cubed. Couldn't you split it up as an I squared times a third I? And isn't I squared negative 1? So it kind of follows the rules, doesn't it? One more. What will I to the 4 end up looking like? I thought I saw your lips moving, Mark, and I think I saw the right answer, or heard the right answer. Do you want to tell us all?
+1.
Is it a guess? Is it a pattern? Or you're right. And how did you figure it out?
I squared times I squared, so -1 times -1.
Good way of looking at it. That makes sense. Now, here's something really fascinating about I and powers of I. That's the only 4 answers you ever get. You might say, well, what about I to the 5? Isn't I to the 5 just the same as I to the 4 times another I? And isn't that 1 times I? Don't you just end up back up here again? So I squared, I cubed, I4. I5, I6, I7, I8, I9, I10, I11, I12. You see, you just go round in circles through eternity. There's no other number, apart from probably 0 and 1, that if you do powers of them, do you get a pattern? Right, 0's boring, right? 0, 0 cubed, 0 squared. Don't you just get 0 all the time? 1, that's not much better, isn't it? Don't you just get 1 all the time? I just thought a third one. Doesn't -1 at least have a pattern? -1, -1 squared is +1, then -1, then +1. Well, this is what I is doing. Kind of cool. Right, let's return back to some foiling. Right, foil. 2i times 2i gets you 4i squared. 2i times this is positive 2i. When you go this way, you get negative 2i. And when you go this way, you get negative 1. Do you notice that these two middle terms kill each other off? And isn't that basically 4 times -1? So that becomes the number -4, take away 1, -5. Do you know it's possible? I've just done it. Isn't it possible to multiply 2 complex numbers together and get an answer that's a real number? No i's in it at all. It's okay. Technically speaking, it's a complex number. Isn't -5 just a very special complex number? It's a complex number with 0 i's in it. And what mathematicians discovered is what we think of as real numbers, right, on a number line, are part of complex numbers. Complex numbers are essentially 2-dimensional numbers. In fact, when you want to draw or plot a complex number, you do it like this. That guy there is 2 plus I. You know, like an x and y coordinate. Complex numbers are 2-dimensional numbers. And complex numbers get used in some of the weirdest places. You might think this is pure algebra, who's ever going to do it? They get used in electronics. And they get used in computer graphics. See, if you can store a place in 2D space using a complex number, do you know that's a much easier way for a computer to handle it? And then you can do all sorts of things like, well, I can't do it because I'm like that. But I'll take a very simple example. Can you imagine a box and you had the 4 complex numbers? See, if you doubled all the numbers, wouldn't you just make a box that's twice as big? See, if you added 3, everybody, wouldn't you just move the box 3 there? So you see, you can move objects around by simply just having the complex numbers that represent the kind of outside of the shape. And then you can do calculations on them. You can imagine a ball getting bigger and a ball getting smaller. Can you imagine things moving from left to right? Simple thing like, do you know if you take text that scrolls, do you know you could program that using complex numbers, and that would give you the effect of movement. So they're not totally useless, right? They do get used in some weird and wonderful places. So let's, God, it's going. Is this still going good? Right. So I'm just going to try and pick some, off the cuff, as weird as I can get. Okay. How about 3i take away 4, negative 2i plus 2. If you do FOIL, negative 6i squared plus 6i, add 8i, take away 8. Now that's not a problem. I don't think that's a problem. And I hope that guy's not a problem. Negative 6i squared. It's equal to a number, right? It's not a complex number. It's not getting an I in it. Okay. What's I squared? What number is I squared?
-1.
Oh, won't negative 6i squared be negative 6 negative 1s plus 6? Does that make sense? So you combine them, and there you go. We're almost finished this. I'm going to be giving you some examples just so that we can be sure that we're good. And I want to just try and play with your brain a little bit. Are we comfortable that complex numbers are a number in the sense that you can add, subtract, and multiply? You notice I haven't shown you how to divide. Divide's a little bit more complicated, but can you trust me, you can actually divide them, right? It's possible, right? That makes them numbers, right? Mathematical concept of numbers. So here's a problem for you. Here are two complex numbers. Which one's the biggest? Two complex numbers. Which one is the biggest? Well, normally, don't numbers have I'll call it a bigness? See, if I say to you 7 and 2, everybody says 7's bigger, right? If I say 3/4 and a half, right? 3/4 is bigger, right? 20 and minus 20, right? 20 is biggest. Don't numbers have a size to them, right? If I give you two numbers, shouldn't one of them be bigger than the other? Agree? Well, unfortunately, it's not true. Complex numbers don't have size. That complex number is, in many ways, no bigger or smaller than that complex number. What that tells us in mathematics is the property of size, right, being bigger than something else, isn't important to be a number, right? Numbers have it, and it's great when they do, but other kind of numbers don't. Complex numbers don't have size. Matrices don't have size. A matrix is what a table of 2 by 2 numbers. They don't have size, right? You can have two matrices with different numbers. You can't tell one's bigger than the other. In fact, the concept of being bigger doesn't make sense. No. Is that kind of weird? That numbers don't need size. The fact that all the numbers you've ever seen in your life had them, can you imagine the first mathematicians were a bit dubious about these numbers? I'm sure that's one of the arguments they would say, okay, you can add, subtract, multiply, and divide them, but you can't tell which one's bigger than the other. It can't be a number. And then the others said, why should size be important? Why does it need to have size? Can't numbers not have size? And the answer is yes, there's no reason. So we are going to have the shortest day ever, because I'm going to give you 4 examples. And I'm going to hang about because there may be some earlier homework that I can do. In fact, maybe that's a good idea. I'll ask at the end. But here it goes. And I'm deliberately mucking about with these guys. To disappear. So in this case, answer is 7. Next one has actually got nothing really that special going on. There is a little thing, but hopefully not too big a deal. 4 take away 4 gets you 0. And negative 3 take away 2i gets you negative 5i. So in this question here, you see the answer only has an imaginary part. Has no real part. Has anybody tried 0 plus 5i or 0 minus 5i in a homework question? And if it hits you back with you're wrong or not? Because it looks like it's taking I. It really shouldn't take 0 plus 2i, right? It should only be looking for 2i, because 0 plus 2i is really not 100% mathematically valid. But move on to the next fellow, number 3. Square root of negative 4, square root of negative 9, square root of negative 8. Right, that one should have been a bit of a challenge. I'm going to do the same that I do in every question. I'm going to turn that guy into 2i. That was pretty easy, right? That guy is going to be 3i. That's pretty easy. That guy is not so pretty. Isn't it square root of 8i? You might have simplified it, but at least for the time being, can we call it that guy, right? Square root of 8i. Now when I do the distribute, 2 times that guy is 6i squared, 2 times that guy is 2i squared square root of 8. That guy is negative 6. This guy is, right now, he looks like that. Okay? If you'd simplified the square root of 8, you would be finished right now, but almost finished right now. And since I didn't do it that way, how will I rewrite the square root of 8 so that I can give the answer in its best form? It does simplify, right?
2 times 4.
Yeah. And tidy it up. Agree? You can almost tidy up. Right. This fella here, I would call 2 root 6i. This fella here, 2 root 6i. Right, so turn everybody into an I. That would always think of that as your first step in any of these calculations, whether it's add, subtract, multiply, whatever it would be, convert them into i's. It's just cleaner and there's less chance of making a mistake. So here goes. A little bit messy, so I'll write it down. 2 square root of I times another 2 square root of I. We'll figure out what that's going to be. When you go this way, it's going to be, well, I could do that in my head, right? Would you agree 3 times that just gets you 6 square root of 6i? Right? Now, if you go the other way, you get another 6 square root of 6i. And then when you go this way, you just get an extra 9. Are we all happy about the pieces? And this one is a messy one. I think these guys are easy. These guys, you've now got 12 of them. So 12 square root of 6i. 9 I'll just leave for a minute. Okay. 2 root 6, 2 root 6, an I and an I. There's a lot going on here, right? Everything's been multiplied. So won't the 2 and the 2 get you a 4? And while I'm at it, won't the root 6 and the root 6 get me another 6? So that's basically 24. And won't the I get me an I times an I get me an I squared? But doesn't that get me negative 1? So what I end up with is negative 24, 12 root 6i plus 9. And since these are basically the same kind of term. I can put these guys together, and I believe the ultimate can't do any more answer is that one, right? There we go. Now, if you were comfortable with these, then you shouldn't have any problems with the homework questions. And where did I put that down to? Where are you? Excuse me. Right. I'm going to have to go back in and find where the heck I put a certain page. There we go. And there we go. Okay. I have them. Right. Well, this is week 5 finished. We only have one more week left, 2 days. And then on the following Monday, we are going to have our final exam. So what's due next week? Oops. Chapter 8. And chapter 8 is all about quadratics. X squared plus 5x plus 4. And some of it you've already had to do indirectly. Haven't we, for instance, had to factor quadratics a lot for various reasons, right? Remember when you had to simplify fractions, you had to factor the quadratics, the trinomials. So you're going to do that again. Then we have to occasionally solve quadratic equations because they turned up in application questions. Well, in chapter 8, you're going to do that again. So chapter 8 is going to be a kind of deja vu chapter because there's going to be quite a few things that you're going to say, wait a minute, haven't we done that before? And the answer is probably going to be yes. You have done it before. But that's not a bad thing, right? It means you go through what to do that. But there is going to be some new stuff there. We're going to look at, for instance, in chapter 8, how to sketch, how to draw a graph of a quadratic. And we're also going to look at a thing called the quadratic formula. And some of you back in high school days, which might have been a couple of years for some of you, maybe a few more for others, will recognize the quadratic formula. It's negative b plus or minus the square root of b squared minus 4ac all over 2a. Remember that word? Okay. That'll be probably new to you because you've forgotten about it. So that's what that is. And then our exam. And it's going to be, I guess I should put the date in, no, not the date, the time. It's going to be on Tuesday, right? Obviously, the first day that we get here. When's it going to start? Although I forgot to put it here. It's not a trick question. When will the final start? Tuesday at what time?
5.
5. And it's going to finish at 8. In fact, won't it feel, do you see all the things you did for your midterm? Can you just think about doing them again? Because that's how it's going to be, right? It's going to be, it won't be visible until Tuesday at 5 o'clock. I'm going to have a Zoom meeting that's, we're all going to be there so we can check that you're doing your thing, and I'm here if you've got stuck on a question. And then when you're finished, you're going to upload it to Canvas. And, that's pretty much going to be the end of it. Now, what else I need to say? But I think that's probably covered all the good stuff. You will be, I'm trying to think what my brain's thinking here. I think what I probably need to do is on Thursday of next week, which will be when we finish these two things, any time that we've got left, and hopefully we do have some time left, we'll devote all the time that we've got to revision for the final, right? So it'll be your chance to say, can we go back and, multiply or divide some fractions? Or can we go back and do one of those votes going up or down questions? So we're going to devote as much of Thursday as I can to review for your final. I'll also send you over that weekend, so it's not this weekend, but next weekend, I'll send you an up-to-date grade on what your score looks like. So you've got an idea of what your grade is before the final. And that'll give you an idea of what you need to pass and what you need to get 3.4 or whatever your goal is. So the last attendance day was going to be on that Thursday. So hopefully everybody's here and gets 100% attendance points. That would be nice. Right, any questions? Today went pretty quickly, didn't it? Did it go pretty smoothly, which is the other side of it, right? You feel good? I guess you'll find out when you do your homework. It's due on Sunday. Shoot me an email as always. I'm hanging about. If anybody has got some questions that they might want to ask, you like one-to-one, and we can do that. Okay, and it's bye-bye from me. Can you say it again, please?
Is the final going to be cumulative?
Yes.
So when we previously,
It will be weighted, it will be cumulative, but it will be weighted with, it won't be like 50-50, right? 50 from the first 3 weeks and 50 from the second. It's going to be weighted more like 30-70. So you'll get some questions, but not that many from the first 3 weeks. And most of the questions will come from, the last 3 weeks. So it is cumulative, but kind of weighted as well.
so when we previously did the square root of -20, it was not real. Will those answers now just be with an I?
Yeah. I tell you what I shall do. I will make sure that if I give you a question like that we only give you the questions that have I's in them now, and we avoid the square root of -4 that you did in the radical world, right? So that you won't have to decide. It will be an I if you see one, right? Okay, that'll make sense.
Thank you.
Okay. Any other questions?
The due dates that you were showing on your screen a second ago, it had section 8 due August 2nd. That really meant to be like
Yeah, the next
7,
week.
right? Okay.
I
Okay, I just wanted to double check.
Yeah, this week all you have to do is up to the 4 sections. I can't remember them. 7, 4, 5, 6, and 7. I think they're called, right?
Oh.
And that's what's due this Sunday. Complex numbers is the last thing you've done. Next week you'll be doing quadratics. There's 4 sections to that, and then that's done. And then the following Tuesday is your final, and that's us done. It's been a short quarter. I think the more I think about it, I just don't know where all the days went. They just kind of went like gone. Oh, you still have it.
I had a question on one of the homeworks.
Sure, that's what I'm here for. Which give me the guy and I'll go looking for him.
It's on 7.7, number 10.
Oh, okay. Number 10, I wonder what I missed. Let's see what I didn't cover.
So I guess I'm confused because I did number 9 and the number is exactly the same in 9 and 10.
And it's not
And number,
liking the answer for 10?
well, the number 9, the answer that I put, it said it's correct, but then that answer choice isn't an option for number 10.
Whoa. Unfortunately, my 9 and 10 might not be yours. My 9 is the square root of -24, and my 10 is the square root of -40. What are your 9 and 10?
My 9 is the square root of -24,
Okay, that's good. And what's
and then 10 is the square root of -24.
Oh God, so they just gave you the same question twice. Okay. Did you stick an I at the end and then work on the square root of 24? And the square root of 24 is 2 root 6 with an I, is that right?
Oh, I put 2i root 6 and it.
Try 2 root 6.
But then it's the same thing as 2 square root 6i.
It's exactly the same. Try it.
Okay.
But try it just in case that's not the problem.
Okay. I guess that's where I was getting confused. So it's essentially the same thing.
Yeah, I mean, you can stick the I. I wouldn't stick it at the beginning. It would look funny, right? I 2 root 6 would just look, to me, it would look weird, right? But
Okay.
2I root 6 and 2 root 6I. I mean, they kind of they kind of look nice. But did you try it? Did you try it and see that it worked? Because
I did it. It works.
So it's been fussy, not about the eye. It'll take an eye from the keyboard, but it's been fussy about where you put the eye.
No, it accepted. It's not being fussy about that. So it accepted 2i square root of 6. So I was thinking that the I would be beforehand, not after, but it's okay to do before or after.
Right, and it said check mark, everybody's happy?
Yeah, it's good.
Okay, so we're good.
Okay, thank you.
Right, anybody get other questions you want to ask? You're still with me, which means you might want to ask me something. So will someone ask me something? It's like in a sci-fi movie where nobody knows you're there and you're staring at me and I'm thinking, am I here or not? Can you see me?
Just out of my own curiosity, like outside of like computer programming, like what applications do we have for complex numbers?
The one that I've been told, I'm not an electronics person, but the one I've been told is that electronics uses it. So since we've got tons of time, why don't I do something about that? Right, I'm going to go on to Google. www.google.com. I'm going to just do a quick search, and the search I'm going to use is complex numbers. And electronics. And I'll see what it hits. Whoa. Okay, hopefully I'll find this relatively quickly and I'll show you the screen. Oh, come on, make my life easy for once in your lifetime. Oh, here we are. Complex numbers are used in phasers, and I don't think they mean Star Trek phasers. I think that's actually a term in electronics. If you get the Ultimate Electronic book, evidently there are complex numbers in it. Introduction to complex numbers in electronics. So, evidently there's a course at the University of St Andrews, which is in Scotland, which deals with complex numbers in electronics. So, guess what? They're using electronics. I can't tell you how they use them. I'm guessing it's something to do with phase shift. You know, there's a vertical and a horizontal. So maybe they use the complex numbers as a convenient way of talking about phases of electric signals or something. I'm making this up, but maybe that's what they do. So, convinced? I mean, just go and look at one of the articles, I guess. Oh, here's one.
Hi, welcome to Wise Guys. This video is behind, and we know that
Oh, God, that's
this point here.
It's something to do with phases. I saw the picture. I don't know if you did. Okay. Any other questions? Mark, have you got one?
I had like one that was like completely out of the realm of like the lesson, but it
You're
was
just
basically on the
interested.
number system.
Sure, I don't mind sharing if other people don't want to. I don't mind hanging about and sharing with us. What's the question?
I was just asking because like complex number systems, I was just basically trying to find out like if in complex number system like it's its own radius, or if it just keeps the radius of whatever number system you're combining complex with.
Well, when you're talking about radius, so you're talking about if you plotted a complex number, as a two-dimensional point, are you talking about the distance that point is from the origin? Is that what you're thinking about?
Well, I was talking about like basically like number systems. If you were to like join it with like binary system by like having a radiax of anything else.
I'm not sure. I guess that's my problem. So you're using the word radius. So could you give me an example of what you're thinking of? Maybe I could, my brain will get.
Like basically like the radiax, like not the radius, like the base of the number system. Like because they say like complex numbers are its own.
Your own number system, yeah.
Yeah.
There's
And
an
so I
example.
was kind of like, okay, well, how does that fit into our number system? Is it?
Oh,
they-
yeah, right. This is how it fits. If you take the general complex number, which is that, and that's complex numbers, and any combination of A and B have to be real numbers. Right? That's a complex number. If you imagine a complex number being written as A plus 0i, that means you've got real numbers.
Okay.
So what that means is that real numbers are just a subset of complex numbers.
Okay.
In fact, there's a little picture that goes like this. There's the natural numbers, there's the whole numbers, there's the fractions, there's the irrationals, there's the reals, there's the complex numbers.
Right.
Complex numbers contain everybody inside it. Real numbers contain everybody inside them. Complex numbers, the difference is that they introduced the I guy, and that kind of increased the number system. It expanded it.
Right.
There's a lot of math out there that is asked, is that the end of making this circle of numbers get bigger? Is there another set of numbers outside of these numbers, right, that we still haven't discovered, right? Another number system that contains complex numbers but is bigger than complex numbers. And they found a guy, I think he was called Hamilton, and they're called Hamiltonians, right, instead of complex numbers. And the guy called Hamilton discovered these, and he found out that it is possible to do it. But what you do is that you basically create 3 versions of the square root of -1.
Mm-hmm.
But they're different from each other. They're not the same thing. And when you create these guys, you generate a 4th dimensional number. And so there is another set out here called the quaternions. The problem with this set, you can add and subtract them, and that's fine. When you multiply them, you get weird answers. Do you know in normal maths, 3 times 2 is 2 times 3?
Mm-hmm.
And in complex numbers, that's still true, right? It doesn't matter which way around I do that, I get the same answer. In
Right.
quaternions, if you take one quaternion, call it A, and you multiply it by another one, B, you don't get the same answer when you go the other way around.
Huh.
And what that tells us is that basically the rules of multiplication die. Add and subtract still survive. They're pretty easy to do. You can imagine adding 4 of these and another 4, right? Add all the I's, all the I's. Add and subtract survives. Multiplication semi-dies. You can still multiply them, but you don't get the same answer. And division disappears. You can't even figure a way to divide
Huh.
because that isn't a consistent way of making it happen. So
Okay.
what we believe now is that we have, and we've always been proved wrong when we did this, but we believe now that we've pretty much came to the end of the line. If you try to increase a number system, say 1 more level, you might be able to do it, but you'll have a number system that you can't add them because it depends on which one you add first to second. Right? You can't multiply them because it depends which you put first and what you put second. Can you imagine a number system like that would be pretty useless.
Right. Or it would only have like one very specific usage and one very specific.
Maybe somebody out there will find a use for quaternions, right? That might well happen. I guess if you were dealing with 4th dimensional space, maybe quaternions would be a nice way to represent something in 4D space.
Okay.
But yeah, complex numbers are typically considered the end of the usable number system.
Right.
Hamiltonians, the next guy up, are not using it. Anything else?
Nope, that was all I had.
Okay, well, you have a nice weekend.
Thank you.
As always, if you get any issues, shoot me an email.
Okay. Have a good
Yeah.
night.
You too. Bye-bye.